previous video, we actually talked about the QIJ, finding the stiffness matrix for all the plies. Only the plies, alright, without the angle yet. Alright, so in this video, we'll talk about the transform stiffness matrix, where we talk about transforming each of the ply into a certain direction, that is in the XY direction. Okay, so previously they are all in their own 1-2 direction, alright, but with their own stiffness matrix. Alright, their own stiffness matrix implies that they are strong in their own they are strong in their own direction. Alright, they are strong in their own direction, I should say that. Okay, but by right this should be in the 1 direction, this is the 2 direction. Alright, because you are gonna pull in this direction. You're gonna the stronger one should be always in the 1 direction. Alright, so this should be in the 1 direction. Likewise, okay, this is correct, and this is correct, except for this one, my class mistake. But anyway, so and therefore what you're gonna do now is to actually transform their own angle, alright, in terms, because they are now in their own 1-2 direction, so I'm gonna transform them into their XY direction, and this is why we're gonna use this QIJ bar stuff. And in this video, it will be very long. Hopefully I can cut short things a little bit. But anyway, so the equation that I'm going to use is this one, alright, your QIJ, alright, and you're going to do it 4 times, alright, it's not do it this 1 time, alright, this is 2nd time, and 3rd time, and subsequently 4th time. No, what I mean 4 times is literally this whole thing 4 times, as you can see. Okay, so this is for the individual plies. Okay, you're gonna so that's why I say the stiffness matrix QIJ is only for the particular ply, alright, in this ply. But if you want to switch it to this direction, alright, you're gonna translate using the transformation matrix, or you're gonna translate the forces, because over here they're taking in forces from, okay, in other words, over here they're orientated in this direction, alright, but the force is acting in this direction. Alright, so we are trying to look for the stiffness matrix, alright, that is against this force, this direction, and this direction, in the X and the Y direction. So I repeat again, alright, although we may the laminar may be arranged in a certain angle, alright, but the force that we are doing is in the X and the Y direction. So what we're calculating for the QIJ bar is to calculate the stiffness matrix where they are subjected to their X and Y direction stresses. Okay, so hopefully this is pretty clear. Alright, and therefore you need to calculate for the angle. So therefore it's a very tedious process. So what I think it would be best if I were to briefly go through this one, or at least you get a feel. Previous video we find for QIJ, so I'll just simply copy it and paste it over here. Okay, so we know our Q12, Q11, etc. are the values, and cosine 4 means that is cosine, it should be cosine theta to the power of 4. Alright, so sine 4 is also same thing, sine theta to the power of 4. Okay, so therefore these are the things, and I don't think it's quite tedious, it's just the calculation part is a bit mafan or troublesome. So I'll just do up an Excel sheet, and then we'll show you the results later on. Yeah, after taking a super ultra super long time, alright, I've calculated for the Excel sheet of the values. Okay, so how does this value works is that if you were to sub in angle 45, for example, okay, which is this one, the first one, okay, this Q11, Q12, everything, alright, will be stored inside this first row. Alright, if I sub in 90 degrees, I'll have them sub in inside the second row. Same thing, the third row and the fourth row, and I'll have all this coming out. Okay, so hopefully this is pretty clear. So I repeat again, for this four statements, if you sub in as 45 degrees, you'll get this row. Alright, I get these numbers. And if I sub in 90 degrees for this equations, alright, I would have this one, the second row, subsequently the third row, the fourth row. Okay, and these are all values for your Q bar. alright, Q11 bar, Q22 bar. Alright, hopefully this is pretty clear. And I just want to highlight also, in additional to certain stuff, is that know that the angles are the most troublesome part. Alright, I would suggest that when you do the question, normally for example sine to the power of 4 theta, correct? So what you do is to actually find these numbers first. Maybe once you find, you have certain numbers, okay? And once you so you subsequently you also need to find other values, cosine. So you have all these values there, and then you can just plug it in and use already. So it will help you to calculate things in an easier way lah. Okay, for example, if I say cosine 2 theta, for example only lah, is maybe 0.5, then this one is maybe 0.5. So once you know that they are 0.5, you know this general equation, you can just sub it in into your equation. You no need to actually recalculate everything again, alright, and type it out. Alright, so you're gonna target all the stuff. Alright, so the things are cosine 2 theta, sine 2 theta, alright, cosine 4 theta and sine 4 theta. That's all. So you calculate these four values first, write it down somewhere. Alright, this is down somewhere. Alright, this is for certain angle, maybe this is for 45, and then you have another one for 90, for 0 and minus 45. Alright, so once you have these things, once you sub it into here, it's easier for you to calculate. It's quite straightforward already. So this is a way of shortcut to reduce the amount of time required to calculate this stuff manually. But nonetheless, these are the answer, alright, for your bars. Okay, the next thing is your A1, or A11, A12, okay, which is coming to the third point. Okay, so Qij bar has been settled. So what I just want to repeat again is that Qij bar is a transformed stiffness matrix. Alright, so previously the Qij is just a stiffness matrix for the ply. These four plies has the same stiffness matrix Qij. However, because of a certain angle, you need to transform them in terms of XY direction. And this is why you're going to use certain angles, 90 degrees, 45 or whatever, to shift them. And in order to shift them, you're going to use this transform stiffness matrix. And that's what we have been doing. Okay, so now what we're going to do is to calculate for the axial stiffness matrix. Axial stiffness matrix implies that you're going to add all this, alright, after you have shift all of them back to their original position, x and y direction, and then you add them up together. That is just the meaning of a axial stiffness matrix. Okay, so it's the total stiffness matrix for your whole plies, all of these plies add together. Okay, hopefully this is pretty clear. By the diagram over here, as you can see, this is the four plies that have been added. Alright, and then it's in the x y direction. Alright, so hopefully this is pretty clear. And that your k is the number of ply. Alright, so you're going to sum them up all together, and then you're going to multiply by h over n. Therefore, your h, alright, your h is actually the total thickness of a laminate, okay, which is 0.04, correct? Because your laminate, alright, if I zoom in, one of a ply is 1 millimeter thick. Alright, so we have 4 plies. Alright, so therefore we will have 4 millimeter. Alright, sorry, I should say it's 4 millimeter or 0.04 meter. Okay, and then divided by n. N is the number of plies, so we have 4 plies. So we will have 0.01 meter or 4 millimeter. Okay, so I just realized, okay, the answer is a bit weird. I also don't know how to settle, but it goes like this. Alright, this thing over here, this is in terms of a gigapascal, correct? So Pascal, if you remember, is Newton per meter square, so it's giga Newton per meter square. Okay, and this portion over here, if you think about it, is a total thickness of a laminate. Alright, so the total thickness talks about in terms of a certain metric, m meter or millimeter. Okay, so in our case, if we change to meter, because Pascal is in terms of meter, so in fact we should get a 0.01 meter. Okay, you get what I mean? So therefore, okay, 4 mm is 0.04 divided by the number of ply, which is 4. So this is 0.01 meter. Alright, so 0.01 meter times this one, our Aij, its unit should be giganewton per meter. Alright, it's only one direction, so it is quite intuitive that it is actually giganewton per meter, okay, because it's in terms of one direction pulling. But however, in our answers that is given, alright, this is otherwise, okay, because the answer given is somewhat this value, alright, and this is our aij, okay. He assumed that the h divided by n is equals to 1, alright, so this means that h is 4 mm and your n is 4, correct? So 4 divided by 4 is equals to 1, alright. So if you're taking 4 mm, this means that we're talking about giga newton per millimeter square, correct? So this, if that's the case, then we're gonna change all the values for your Q into a larger value, alright, because they are in giga, okay. So if you want to switch back to meter, then you're gonna be 10 to the power of 12. Alright, giga is 10 to the power of 9. So there is some units somewhat contradicting each other, and the answer, it's a bit okay. The answer is this answer, alright, for your aij, alright. So rest assured the answer is this one, okay. However, if you think about it, for the SI unit, something is wrong somewhere. So in the future, if you can update, you just update over here. But anyway, so in fact, alright, aij is, what should I say, man? I a bit checked already. Okay, so this portion aij has two portions. You're gonna sum out all the qij, okay. So I sum all of this, I will have this value. I sum all of this, I will have this value. I sum all of this, I will have this value. Same thing, this value, okay. And why am I saying that this value is A11 is because h divided by n is equals to 1, okay. And this is why aij is equals to summation of qij, and that's it, alright. But however, alright, if you think about it, if h over n is equals to 1, this means that this h, alright, this thickness of a laminate is 1 meter, alright. You know why? It's because all these q's are in terms of a gigapascal, which is in terms of meter, alright. If you're talking about that, then this thing should be in meter also, because everything must be consistent. But that's the problem, because our thing is in terms of millimeter, and this is why there is a problem out there. And yeah lor. But nonetheless, this is our aij that is from the answer. So we have somewhat solved for our axial stiffness matrix aij. And just to update, we are somewhere here, alright. We have solved for that already. We have somewhat add all the laminate up and know that the x-axis and the y-axis, this axial stiffness matrix has been found, which is aij. Now is our final one which is trying to calculate the longitudinal x, alright, Young modulus, which is the E. So in order to calculate this ELX and the shear modulus gxy, then you can just simply apply the formula, okay. And these are the formulas that you are required, and so therefore you can just simply sub it in, and that's all it is, alright, for your values. So if I were to sub it in, my values, I'll just write it down over here. Take note, this is A11, this is A12, A22, and A33. Sorry, this is A33. My fault. This one should have value, okay, it's not 0, alright, it have some values, okay. So yeah, there's certain careless mistake. And after this careless mistake, I just realized also that besides calculating, just now I say calculating for this individual values for yourself, or you can also calculate straight away all these things, this Q stuff, because all these are just values, all standard values, because Q11, Q22 are all the same for all of them, different angles. Over here this is 90, this is minus 45, right? But different angles only talking about the cosine and sine, which is only the cosine square, sine square, cosine 4, and sine to the power of 4. That's it. Alright, as for the Q1, Q22, the addition, you can also calculate itself. Alright, so it's easier for you to do things. Yeah, this video sucks, but yeah, never mind. So nonetheless, if I were to solve it out, alright, I think it will have a better accurate answer, so give me a while. it is 21.227 for your shear modulus. Longitudinal is this. Okay, there is some discrepancy against the actual result. Alright, the one contributed by the lecturer, these portions are the same. Okay, and give me a while. The only difference is this value, which end up this one also has some discrepancy. Alright, it's only these three values that has problems. Alright, this one is 28, or the lecturer's value is 28. I think my Excel sheet something wrong, I think. And this one is 69. But nonetheless, this is somewhat the way of solving things. Alright, and this is what they want, longitudinal modulus in the x direction. Longitudinal, Lx is longitudinal in the x direction. So it's the modulus. And what it means in total is telling you that if I were to draw all the 4 plies, so this is the x, this is the x, this is the y axis. So the longitudinal axis is talking about this longitudinal in this direction, in the x direction. That's all it's trying to say. So it's ELX. Alright, the total Young modulus for this whole piece of laminate, all the ply add up together. So yeah, and then the shear modulus is just to shear the whole 4 plates. Alright, all the 4 plies add together. So when you shear them, this is the shear modulus. Okay, and this is it for the last part of our thing. Alright, it's a little bit blur here and there, but hopefully this makes things quite clear, I guess. So yeah, this ends the question on question 5. The answer is 46.5 and 17.3. Okay, so our answer is a little bit, the one is 46.5, 17.3. So there's quite a big differences. This one's still okay. This one, yeah, that's why I say need to check it out. But yeah, so see you in next video on tutorial 2 question 1. Yeah.